All right, guys. So we're going to go over some vectors. This should be a very quick review for everybody that's taking pre-calculus, which should be everybody in this class. Okay. So when we have a vector, we know a vector is an arrow, right? Array. And this would be the head of the vector. This would be the tail of the vector. So all we're going to do is practice adding vectors as we should have done before. Okay, so let's go ahead and do a quick review before we go into how we use this in 2D motion. So starting at the X right here, right? We're going to walk 5 paces to the east and draw a displacement vector. So we always start at the tail and move toward the head. Right, so never oh, it already tells you. Never mind, my bad. So northeast, right? We're going to go up to 5. That's where we're going to end our vector. So just like this, we're moving 5 paces and we're going to draw the head of our vector over here. Okay. Now, that would be vector R1. Okay. Now we're going to draw a second vector. So the student turns left and walks 5 paces north. Now, when we draw an addition of vectors, right? So we moved 5 east. Now we're going to move 5 north. We're going to go from head to tail. And we're going to move 5 north. Boom. Right? Oops. That came out. Let's see. Just like that. Now, this would be 5. 1, 2, 3, 4, 5. So we'd end at 7. That's going to be vector R2. Okay? Now we have the vector representing the total displacement starting from X and ending at the final position. So this is going to be our displacement vector. Remember how we talked about our displacement being the shortest path? It's going to be the vector with the shortest path. And if you remember from adding vectors in pre-calculus, you have head to tail, and then from beginning, first point to final point. That's going to be our resultant vector. Right? This is going to be our resultant vector. So that's going to be R total. So we know the length of the first one was 5, and we know the length of the second one was also 5, right? So what does that make our total? Now, this would be if we add R1, R1 plus R2, right? If we add them up, we should end up with 10. 5 plus 5 is 10. This is going to be the biggest rule in this class, and you'll hear me repeat this over and over and over and over again. 5 plus 5 is not 10. 5 plus 5 is not 10. Not when adding vectors. And the reason for this is, what shape is this? This is a triangle. Right? Triangle, what do we know about a triangle? A squared plus B squared equals C squared. So does 5 squared plus 5 squared equal 10? No, absolutely not, right? 5 squared plus 5 squared is going to give you the C squared. So it's going to be 25 plus 25 equals, my bad, equals C squared. So square root, we're going to get the square root of 50, right? Square root of 50, this is 25 times 2, right? So 25 times 2 square rooted, 5 square root of 2 is actually C. So 5 plus 5 does not equals 10. 5 plus 5 equals 5 square root of 2. Okay? So how should we always, let's make some rules, right? How do we always draw vectors being added from head to tail? Right? And how do you draw the resultant? From initial point to final point. And one last rule. How do we add vectors? We're going to say by components, as we did in pre-cal, right? Or Pythagorean theorem. Okay? So, the biggest rule of this class, 5 plus 5 is not 10. Now let's go ahead and let's apply some of these things. All right, so we're going to start working in 2D. Now, we've learned that d equals v naught t plus half a t squared. D is displacement, v naught is velocity at time 0, so velocity initial. A is acceleration, t is the time elapsed. Let's answer the following questions. Okay? So, which ones are vectors, which ones are scalars? So we went over this already, right? Vectors, scalars. This is a quick recap. You guys should be able to solve this on your own, but let's go through it. We know that displacement is a vector. We know that velocity is a vector. We know that time is a scalar because it's only positive. And we know that acceleration is also a vector. So, what does multiplying a scalar times a vector do to it? So, let's say we were moving 20 meters per second. So, this would be a velocity. Velocity, which is a vector. Right? And we multiply it by 10 seconds. Right? Which is time, which is a scalar. Right? We're going to end up with 200 meters, which is displacement and a vector. So when we multiply a vector by a scalar, we end up with a vector. So what happens when we multiply vectors and scalars? You get a vector of a different magnitude. So lengthened or shortened the vector. Sorry that I'm not at Khan Academy writing skill levels. All right, rewrite the equation noting the quantities that have direction with an arrow. So this is just the proper way to write a vector equation. So d equals v naught t plus half a t squared, right? Displacement is a vector, velocity is a vector, acceleration is a vector. That's all we have to do here. So it looks just like this. Now, we got to know the units of these. So we have displacement. What are the units for displacement? We talked about this. It was meters. Velocity was meters per second. All right? So that means that v naught t, sorry, let's do this. So v naught t is meters per second times seconds. Seconds cancel. We end up with meters again. Right? And then our last one, which is half a t squared, we get this is a scalar, so this is no unit. Meters per second squared times seconds squared. We end up somehow with meters again. So we ended up with 3 units of meters. And meters, so all of them are in meters, and meters is for displacement. Now, how many displacement vectors do we have? We have 3. All 3 were displacement vectors. All 3 were displacement vectors because they all ended up having the same units. So now if we were to do a head to tail, if we know that D equals V naught T plus half a T squared, let's practice our head to tail. V naught T. Go here, that's 1, right? Then we'll add our second vector, so head to tail, we add, and now our resultant vector, our displacement. It goes from beginning to end point. So we can turn this equation literally into an addition of vectors. So yes, it is consistent. It follows vector addition rules. So we're adding three displacement vectors using our vector addition rules. On the other vector triangle, circle the initial and final positions, and then draw the actual path of the object motion. So now what happens is we have our total displacement was this way, but it was shot up at an angle. This is our initial velocity. And then it went straight down. This is our acceleration. So this is actually an object being thrown. It was thrown up at this angle, and as it travels across the room, it goes back down. So the acceleration was constantly downward while the object was moving across the room. What I usually do is I throw a marker at a student at this moment. So if you want, play catch with your friend, and you'll see that as you throw it up, it accelerates downward all the way through, and you end up with your displacement in a straight line. If you were to stop the displacement at the top, so you threw something, right? When you make it to the top, what happens? This is the point here where there's no upward velocity, right? So at this point, each one of these is a little displacement vector, right? Every single one of these has acceleration downward, right? This one is this way, displacement, right? So every single one of these is a vector. Every single one of these is a vector of velocity. So it has an x and a y. So in this point, this would be the velocity in the y. This would be the velocity in the x. This would be the total velocity. And the same thing goes for all of these. Now the vector triangle for this one at the top, remember when we get to the top of a ball being thrown up and straight down, what happens at the top? It stops moving. But can we say that this ball stopped fully moving? Throw a ball across the room and think about it when it's at the top. Or grab anything in your room and just toss it. When it's at the top, you'll notice that it's still moving horizontally. It's still moving in the x direction. It's just not moving up or down in that moment. At the top, the velocity in the y is 0. But the velocity in the x is the same, because nothing was slowing it down. Okay? And then at the bottom, you can make your own rules. Think about it. We're going to go ahead and practice. This was the answer, by the way. It's just going to be a straight line. We're going to go ahead and do some practice problems now. If you have any further questions on how 2D motion is just vector addition, feel free to email me or send me a message on Remind.